Good morning, good afternoon. It is my great pleasure to introduce today's ISQGD distinguished speaker, Professor Kenneth M. Golden, an applied mathematician whose work has helped shape the modern mathematical foundations of sea ice science and its role in the climate system. Professor Golden is a distinguished professor of mathematics at the University of Utah, and he also holds an appointment as adjunct professor of biomedical engineering. Professor Golden's research centers on the modeling and simulation of complex multi-scale systems arising in geophysics and materials science, with particular emphasis on sea ice as a composite material. His work draws on ideas from composite materials, statistical physics, phase transitions, diffusion processes, inverse problems, and remote sensing, connecting rigorous mathematics with major scientific questions about polar processes and a changing climate. A hallmark of Professor Golden's career is the close integration of mathematical theory with field science. He has participated in numerous polar expeditions to the Arctic and Antarctica to obtain data that inform and validate sea ice models, and he is widely recognized for exceptional interdisciplinary leadership and scientific communication, including extensive invited lectures internationally. We are deeply honored to welcome Professor Kenneth M. Golden to the ISQ Distinguished Lecture Series, and we look forward to an inspiring lecture on multi-scale modeling at the interface of mathematics, sea ice, and metamaterials. Please join us in warmly welcoming Professor Kenneth M. Golden to the ISQ Distinguished Lecture Series.
Great. Well, thank you so much, Mrinal. Let's see. Let me share my screen with you. Okay, there we go. Okay, you guys can see this?
Yes.
Okay. Well, anyway, it's a real pleasure to be able to speak in this distinguished lecture series. I really appreciate the opportunity. So I'm going to tell you about, I guess, work I've been involved in literally since high school, where I got my start on sea ice with working at NASA in like 12th grade. And then in college, I studied sea ice as well at the Cold Regions Research and Engineering Lab. And it certainly guided my research throughout most of my career. So I'm going to tell you about multi-scale models for sea ice, but also a much larger sort of field of composite materials and metamaterials that of which sea ice is a specific example. And what you're looking at here is a field of pancake ice in the Southern Ocean from the Australian icebreaker Aurora australis. And this kind of pancake ice forms in wave fields, and you see a few waves out there. So sea ice itself is a multi-scale fluid solid composite. It has composite structure at the microscale, these sub-millimeter scale brine inclusions. On the surface of Arctic sea ice, you have melt ponds, which sort of divide the surface into this composite structure of fluid and solid. And then the ice pack, and on much larger scales, on the scale of the Arctic Ocean, the ice pack itself is a granular composite where the grains, a granular composite of ice flows in a seawater host where the grains range in size from a few centimeters up to 100 kilometers. And as I mentioned, sea ice is an example of a composite material, and composites appear throughout science and nature and industry and medicine and all sorts of building processes, industry, and so on, engineering. Here are a lot of different kind of composites like plywood and concrete. Here's a porous rock. Here's sea ice. And then several years ago, I mean, I don't know, maybe a couple of decades ago, they started making onto the scene these strange materials called metamaterials, strange composite structures called metamaterials, which are kind of thought of as media that exhibit macroscopic properties that are not normally found in nature. And so these negative index of refraction materials here, I'm sure you're aware of Snell's law, but at an interface between air and water, Snell's law tells you the angle at which the light bends. But with negative index or refraction materials, they bend the wrong way. But then you can have all kinds of amazing applications, such as making things invisible, like Harry Potter's invisibility cloak. But of course, there's spin-off companies and all sorts of actual applications and industrial and defense type of applications of electromagnetic cloaks, as well as acoustic cloaks or seismic cloaks. There's all sorts of applications, obviously. Okay, so one of the central themes in this entire business is how do we use small-scale microscopic information to find the effective behavior of the system or the material relevant to large-scale, in the sea ice case, sea ice physics and ecology models. Or in the case of composite materials, what's the effective behavior? How is that material going to behave in your applied setting? So the underlying word here, I guess, is homogenization. Forward homogenization is where you have information about the composite materials, such as the volume fraction of the little inclusions, the brine inclusions in sea ice, say the electrical conductivity of the brine and the ice. And then you're interested in getting information about the overall or effective conductivity on the much larger scale. The forward problem is where you have information about the micro scale, and you use that to get information such as rigorous bounds on the macroscopic or homogenized properties. And the inverse problem is where you make bulk measurements of the effective properties and then try to figure out what was inside the black box. What is the micro scale? What's happening at the microscale? And these problems have a very long and storied history. Maxwell and Einstein worked on these problems of dilute spheres and looking at their effective properties. And there's been tremendous advances, particularly throughout the 20th century into the latter part of the 20th century, I would say, and into the 21st century. So this might remind you of something you learn in like Physics 101, where you look at resistors in series or resistors in parallel. And in series, they add for the equivalent resistance or the effective resistance, and in parallel, the reciprocal sums in series. But of course, we're not interested in such simple geometries or microstructures. We want to consider, for example, an infinite lattice where there are two resistances which appear randomly with, let's say, a probability P or 1 minus P. And then the question is, what is the effective or equivalent resistance of this infinite lattice, which of course is a very difficult problem. And there's a very large physics literature in the physics in theoretical physics concerning this. Another large area where we mine ideas and methods is statistical physics. Solids, liquids, and gas, and the transitions between these different states. And I was lucky to be involved in a Nature Reviews physics paper where the idea was to lay out how novel ideas in physics are being used to study the cryosphere, all the different aspects, not just sea ice, but all the different the frozen portion of Earth's surface. Another large stream running through our research program is polar ecology and the inextricably intertwined notion that how life evolves on the sea ice is inextricably intertwined with the physics of the ice and the microstructure and its the physical habitat. In particular, how do ice properties affect the life that it hosts, and vice versa? How does the presence of life in and on sea ice affect the physical properties of ice? And as you'll see, it really does. So what this talk is about is kind of a tour of recent results on multi-scale modeling of the physical and biological processes in the sea ice system and composite materials more generally, because I am a mathematician, and when we prove theorems or develop methods to study sea ice, well, often there's nothing special about sea ice. We're just using ideas from physics and math, so we could apply those to other systems and materials. And we're going to go from the micro scale to the mesoscale to the macro scale. And interestingly, we will encounter an unusually broad range of topics in mathematics and theoretical physics, including some of the main topics of interest to this group, which is fractals and dynamical systems, and actually and even quantization, because there'll be connections with quantum mechanics and the Hamiltonian as well. Okay, let's focus on the microscale. So as I said before, as you freeze seawater, you can't incorporate the salt into the crystalline structure. And so you have these little millimeter scale, sub-millimeter scale brine inclusions. And each one of these little inclusions can be an ecosystem in itself, containing algae and bacteria, viruses, nematodes, all sorts of things. Here's the brine, some of these brine inclusions from scanning electron microscopy, looking on very, very fine scales. And then this is basically a 10-centimeter vertical section showing some of the fractally tree-like structures that you see. And then if you slice this horizontally, this is kind of what you'll see is again, which actually kind of looks like diffusion and limited aggregation. Okay, so fluid flow through this porous microstructure in sea ice is incredibly important for so many of the physical and biological processes that occur in sea ice, such as the evolution of these melt ponds on the surface. And getting these melt ponds right is really important to long-term predictions of what's going to happen to the sea ice, because the ponds determine the albedo, or the reflectivity of the ice, namely how much solar energy is absorbed versus reflected. And as I mentioned, the sea ice, the brine inclusions are ecosystems, and you get these incredibly dense blooms of algae. There's an algal cell inside of a brine inclusion, but their nutrients come in through fluid flowing through the porous microstructure. So that's one of the main ways that the physics of the ice strongly determines what's actually happening in these algal communities. Prior to our work, back in around the early 2000s, glaciologists would take photos, I guess, of the brine microstructure of sea ice, try to piece them together. We were the first to develop an X-ray tomography method and then be able to analyze everything mathematically. So this is about a centimeter across. Notice that it's cold with only 3.3% brine. No pathways, warms up a little bit. There's one tortuous pathway that goes through these bottlenecks, and then many, many pathways. So the connectivity and geometry and volume fraction of the brine inclusions depends very strongly on temperature. So this brings us into percolation theory, where here's the basic 2D percolation model, because essentially we're looking at effectively a transition in the connectivity of the brine phase of this porous medium, and that directly leads us into because that's originally what percolation theory was developed for looking at sandstones. And so here is the 2D square lattice. About a third of the bonds are filled. The bonds are where fluid or electricity can flow. Here's 2/3 of them are filled, and we're really imagining an infinite lattice. And so there is an infinite conducting or connected pathway through this entire lattice. But the real question is, what's the smallest value of P such that you have the appearance of an infinite connected pathway through which fluid can flow? And let's see. And so in percolation theory, there's all these beautiful predictions. So here's the effective conductivity, or in a similar graph for the fluid permeability. Below the threshold, there's no fluid flow or electricity. Then it takes off with a critical exponent right near the threshold, and then goes up. And the conductivity exponent is called T. The permeability exponent is called E. For lattice systems, they're equal to each other. In 2 dimensions, the best numerical value is about 1.3. In 3 dimensions, it's about 2 for the conductivity critical exponent. Early in my career, I did a lot of rigorous mathematical work on trying to get rigorous bounds, at least for a model of the backbone. And what was interesting was that my upper bound of 2 correlates quite closely with the best known numerical estimate in 3 dimensions for the conductivity or fluid permeability critical exponent. Now, in the continuum, such as so-called Swiss cheese composites, which is not a lattice for sure, you can get non-universal behavior. And of course, you have to ask that question for sea ice because sea ice is a complex continuum material. However, amazingly, it will turn out that the critical exponents for permeability and conductivity in sea ice were able to show that they should be the universal lattice values, which indeed correlates with the data. But getting your hands on the threshold was one of the first big kind of mysteries, essentially. In other words, these 2D lattice models predict a value of about, the threshold here is exactly 50% or 1/2. In 3 dimensions, it's about 25% or something. However, in sea ice, it's about, in columnar sea ice, it's about 5%. So below 5% porosity or volume fraction of the brine inclusions, the sea ice is effectively impermeable in the vertical direction, and then permeable and increasingly so when you get above 5% brine volume fraction. And that threshold of 5% corresponds to a critical temperature of -5 Celsius for a typical bulk salinity of 5 parts per thousand. Hence, this finding has become known as the rule of fives. However, how in the world do you predict this? Why is there such a mismatch between what these lattice models predict, excuse me, and what we find, excuse me, and what we find in the actual sea ice? And this shows you how dramatic this percolation threshold is. Namely, this is an autumnal algal bloom, and this is the threshold. In other words, you're getting nutrients, and then all of a sudden, the algae find themselves in impermeable ice, and the bloom just shuts down. Excuse me. So that's one of the very important ways that the physics of the ice controls the evolution of these microbial communities. So then, as I was mentioning, there's this real mystery. How in the world do we predict the 5% threshold? Well, it turns out that I was able to use the percolation theory for so-called compressed powders, where you take big polymer spheres and little metal particles and squash them down. And then the percolation threshold can be calculated as a function of the ratio of the particle sizes. And then I sort of imagined the sea ice microstructure to be uncompressed and go back to the foundations of this compressed powder theory. And the percolation threshold is then a function of the ratio of the particle sizes. And if you just do a few measurements on the sea ice microstructure and plug it into this percolation theory developed by Kuzi and Turner and Malieris, back in literally the 1970s, then out pops the 5%. But what's so interesting is that these compressed powder composites formed the foundation of so-called stealthy coatings for aircraft, so that aircraft can be cloaked from not light, but radar, microwaves, as we're all aware of. This is an example of what I like to call cross-pollination, where we take ideas from seemingly unrelated areas of science and technology and engineering or medicine, like stealth technology, and we apply that to understanding the physics of sea ice. Anyway, so here's another example, is that the microstructure of sea ice is very similar to the microstructure of human bone, and we took some of the mathematics that we developed for analyzing the connectivity of the brine phase in sea ice, analyzing that, recovering that electromagnetically, and developing a new method for monitoring the onset and progress of osteoporosis. Because again, the math doesn't care if it's sea ice or bone or whatever. It's just math. Okay, so the next big step was, well, what does percolation theory predict about the fluid permeability? And so, as you saw in that earlier slide, there's like a power law behavior as the permeability takes off from the threshold, with the best value, the critical exponent of 2, there's the 5%. Now, this might look like a fudge factor. However, this scaling factor in front is actually, we theoretically predict that from the X-ray tomography. and a theory called critical path analysis, which was developed by Amby, Gauker, Halperin, and Langer, AHL, in the theory of transport, electronic transport in doped semiconductors. And again, that's another example of cross-pollination. And so we applied that theory, the critical path analysis, to figure out what that constant is, and then we're able to confirm my rule of fives and the theory that we get from percolation theory predictions agree very closely with field data that we took in the Arctic. This is the cover of the notice is the AMS. I didn't know that picture was being taken. That's why it's kind of a good photo, I guess. I had no idea it was being taken, and that's me doing the first measurements ever of fluid permeability in the Antarctic ice pack. And of course, this is the notice of the AMS, a big scientific journal. And you would think that these people here were conducting very important experiments, but in fact, they were playing soccer. I was there and I saw it. The idea is that we drill these partial holes in the ice and then we watch water fill in the hole. And we've developed all kinds of methods to measure the level of the water. And actually, what I'm doing, this was the first method. We had such thin ice, I was able to do everything with just my watch, like a diving watch and a ruler. And of course, we advanced a lot from there over the years, but that was the start. This is some of our electrical measurements that we did in conjunction with the fluid permeability measurements, because the electrical properties are intimately related with the fluid properties. Now, so this theory that I've just laid out of these power law implications for the fluid permeability as a function of porosity. So that's all well and good when there's no algae there. However, the algae display very interesting strategies for living in this very extreme environment that they live in, with wild fluctuations in the salinity of the water, the temperature, and so on. And so they secrete extracellular polymeric substances, EPS, which ultimately significantly affects the geometry of the brine microstructure. So we have to ask the question, how does the presence of EPS affect fluid transport and nutrient transport processes? In other words, how does the biology affect the physics? Here, some of this EPS has been stained blue. There's a pinnate, like a pen-like diatom. And then here's without EPS, and you can see with EPS, the presence of EPS makes the brine microstructure more fractally, and it changes a classic log-normal distribution into a bimodal log-normal distribution. And so one of my PhD students, Kyle Steffen, he developed like what we call a random pipe model to try to model all this phenomena, and amazingly was able to develop, work out some rigorous bounds analytically on the permeability. And literally just this week, we submitted our first paper with Anthony Jage on a dynamical systems model, not just of the nutrients and phytoplankton, but the nutrients, phytoplankton, and EPS. In other words, how does the presence of EPS regulate these algae blooms? Okay, we've with Lou Kondich and Manav Arora at New Jersey Institute of Technology. We've been taking our brine X-ray tomography and we've been skeletonizing it so we can basically do computational topology, revisit some of our percolation concepts, critical exponents. There's a lot of interesting questions that we can ask concerning the brine microstructure and its connectivity and other geometrical features and topological features. This is a different kind of skeletonization that we've tried. There's various methods that we're looking at. Okay, so going back to the early 1990s, I was involved in a large Office of Naval Research project on the electromagnetic properties of sea ice to develop next generation inverse scattering algorithms so that satellites up in the Arctic could look down on the ice pack and figure out what's going on, how thick is it, and so on. And I was sitting there with a bunch of sea ice optical scientists, and we were all saying, yeah, the brine microstructure, boy, it looks like fractals. This is probably about 5, 6, 7 years after fractals had, been introduced to the world by Mandelbrot and so on. And but actually, up until a few years ago, nobody had asked the question, to my knowledge. And so I work a lot with undergrads and high school students, as well as PhD students and postdocs. And one of my amazing undergrads, Nash Ward, I threw him at this problem into gigabytes and gigabytes of complex X-ray tomography data. And immediately, within a month, he started getting some really interesting results about the fractal properties of the brine phase of sea ice. So here's a classical problem of the fractal dimension of the coastline of Great Britain by box counting, where the rate at which the number of boxes goes off to infinity is measured by the fractal dimension. And so, much to our surprise, we found what to me was very unexpected. Here, this red curve is the exact result for three-dimensional, exactly self-similar fractals, such as the Sierpinski tetrahedron, or there's the 2D version of the Sierpinski triangle, of the fractal dimension as a function of the porosity as you go through the different levels, say of the Sierpinski triangle. But here's our data, and it fell right on that curve again, which I just didn't expect, and we didn't believe it for a while, and it took quite a while to really sort through all this and actually believe it because it's so beautiful. Then amazingly, another freshman of mine who started with me a couple years ago when she was a 12th grader, she on her own started asking these critical questions about melt ponds and asked some questions that I felt kind of embarrassed that I hadn't asked before. And on her own, I think probably just within a week before she was supposed to give a big presentation on her freshman fall research project, she found an astounding result. Let me remind you of this. There's that red curve. Here the red dotted curve is that same curve, but in 2 dimensions. And then the blue is actually data from simulated melt ponds that we know correspond to reality. And she's actually just, I guess, probably a week or two ago, Natasha was able to do fractal dimension calculations on real melt ponds, and lo and behold, the data fits right along, just like this, the data fits right along the curve. So anyway, now we have to rewrite the paper because it's like, are melt ponds big brine inclusions, or are brine inclusions tiny melt ponds? In other words, from my perspective now, oh yeah, as I always thought, they're kind of the same. They have the same geometrical scaling laws, which I find fascinating. This is a hierarchical picture of, say, a core of ice, and then blow up a little piece, and then take a little piece of that. So this is 2 millimeters by 2 millimeters, just simply chronicling all the different kind of critters that can live at this micro scale: bacteria, diatoms, flagellates, rotifers, nematodes, and algae, and so on. Okay, so another very large part of my research program has been, which actually is when I started, that's how I got my real start, was studying the electromagnetic waves in sea ice when I was in college to measure the thickness of the ice. That was the application then. We're interested in the homogenized electrical properties, the effective complex permittivity of a composite in the quasi-static or long wavelength regime. These are the quasi-static Maxwell's equations. Here's the constitutive law, divergence-free, curl-free, and then this defines the macroscopic homogenized parameter, epsilon star, which of course is a tensor. And it's a complicated function of the ratio of the constituent parameters, the brine and the ice, and the composite geometry. And the method, this is a method that goes back, developed independently by David Bergman and Graham Milton. And then George Papanicolaou and I, my first year graduate school, worked on the underlying functional analysis and mathematics. And that's actually where the connection with quantum mechanics comes in. And so this is a deceptively simple looking Stiltschi's integral formula for the effective complex permittivity, where one of the important mathematical aspects is all the parameter information is embedded in this complex variable S, but the complexity, all the geometry of the composite is encoded or distilled into this spectral measure of a self-adjoint operator gamma chi, where gamma is gradient inverse Laplacian projection down onto curl-free fields, and chi, this is where all the geometry comes in, 1 in the brine, 0 in the ice. And we're able to get rigorous bounds, approximations, and develop an inverse theory based on this integral representation. And again, the basic idea is that the complexities of mixture geometry are encoded into this spectral measure. And this is and basically everything can be computed from the eigenvalues and eigenvectors from a discretization of this operator gamma chi. So gamma chi plays the role of the Hamiltonian in quantum mechanics. The geometry of the composite is analogous to the details of the potential energy function. Here are rigorous bounds, the outer bound, so using the Stiltschi's representation, only assuming volume fraction, here only assuming isotropy, and then the solid bounds are where you assume a matrix particle geometry, where you assume basically that the brine does not percolate, and then you get a spectral gap, and you can get much tighter bounds. And we've also gotten inverse bounds on the porosity, but from bulk permittivity measurements. And also then this was a pretty involved piece of work where we were able to get the first rigorous information about particle separations from bulk permittivity measurements. Another one of my amazing high school students, this is Clara Platt. She started with me as a 10th grader, and now she's in her freshman year, and she's already 3/4 the way through the math major, and she's working on Stiltschi's integrals and spectral theory and now uncertainty quantification. So the classic theory is where you assume the porosity or the volume fraction of the brine, but in reality we don't. There's a lot of variability, and so she assumes that the porosity satisfies a Gaussian, and then she can get like the most likely regions within a bounded region as to what would be the most likely values of the homogenized parameter. And then also she can do this in the matrix particle case. But also this work has gone a lot further in that she's looking at these so-called matrix particle bounds and looking at the largest eigenvalue and looking at the uncertainty in the spectral gap. And she would be found an amazing analytical curve, which anyway, it's pretty spectacular. And so there's another a math PhD student that's also intimately involved in this particular project. So of course, sea ice is a polycrystalline material like a rock or like metals. And another PhD student, Adam Goley, was able to push through an extension of the Stiltschi's framework to polycrystalline materials. So the underlying math is very similar, but it's different. And instead of the geometry of the composite, you have statistical information about the orientations of the crystals. And so we were able to get forward and inverse bounds. And then and we're particularly interested in the difference in electrical properties between columnar ice and fine-grained granular ice. And actually, this is the cover of the Proceedings of the Royal Society, where we published this first paper on this. And literally what is it, February 28th, just a few days ago, we finally published the paper that shows that, well, one of the reasons why we're so interested in granular ice is because it has a much higher percolation threshold, totally different fluid flow properties. It affects all the biogeochemical modeling, the ecological modeling, the physical modeling for melt ponds. And so a lot of people have been waiting a long time for this result. I conjectured it in 1994, The conjecture was published with my rule of fives in 1998. We did the first real experiments in 2007, but didn't get what we couldn't do the full-blown thing. Finally, in 2012, we did the experiments and were able to really definitively show with extremely strong evidence that the threshold for granular ice is about 10%, which is of course much higher than columnar ice. And again, this was just published in Scientific Reports just a few days ago, at least the online version. But again, we're very interested, because of this, we're very interested in the inverse problem, namely electromagnetically distinguishing between columnar ice and granular ice from the point of view of complex permittivity. Okay, so given this method that we've developed for computing the spectral measure through, and again, that's a whole nother couple of PhD theses as to how you do all those calculations. But we pushed all that through. And then in fact, I guess there were other methods of computing the spectral measure, but we did it kind of what I call the naive way, where we just turn the gamma chi into a matrix and calculate its eigenvalues and eigenvectors. But what we did not foresee was by doing it that way, we could compute statistics of the eigenvalues and the eigenvectors. And that led us into yet another field of mathematics that I never expected to wind up in, random matrix theory. So in other words, when we computed the spectral measures, and in particular, here's the spectral measures, here's the ocean phase, the ice in the ocean. Here the ocean phase is disconnected. Here it's developing long-range order, trying to percolate, and it finally percolates, and we get the appearance of a pole or an eigenvalue at the origin, which is what we normally see in composites. But what was totally new and unexpected was we were able to look at the statistics of the spacings of the eigenvalues, just like in quantum mechanics. And so basically, when the ocean phase was disconnected, nothing really happening. The eigenvalues are uncorrelated. The eigenvectors don't talk to each other. However, as we develop long-range order, we transition. The eigenvalues repel each other just like electrons on a line. And literally, that's not just a qualitative statement. That's sort of one of the models in random matrix theory. And you get level repulsion, and we transition from Poisson-like statistics to so-called universal Wigner-Dyson distribution. And actually, there's a corresponding Anderson-like localization transition, like in wave localization problems, which I'll talk about at some length. So Wigner and Dyson were the first to enter into random matrix theory and use that to describe the statistics of the quantized energy level of heavy atomic nuclei. But also, interestingly, these so-called Gaussian orthogonal ensembles or Gaussian unitary ensembles that describe the situation, the GUE comes up, it turns out, I don't think anybody's proven this, but it turns out to describe the spacing distributions of the zeros of the Riemann zeta function. So, we're finding these interesting Wigner-Dyson universal distributions in sea ice physics, but it also comes up in the study of the Riemann zeta function. Okay, so as I mentioned, or tried to allude to this interesting phenomena of the transition to universal Wigner-Dyson distribution for the eigenvalue spacings is just a glimpse, a small piece of a much larger picture that we discovered. Namely, we have all the mathematical and physical hallmarks of Anderson localization, which is a disorder-driven transition from like a metal to insulator and back and forth that Anderson won the Nobel Prize for. However, this is in wave physics, where there's honest-to-goodness waves. Remember, we're in the quasi-static regime, where there's no interference or scattering effects. So what we're finding is a percolation-driven Anderson transition, but for classical transport in composites. We see mobility edges, localization, universal spectral statistics. Again, all the things that they see in honest-to-goodness localization. But the amazing thing is we're not doing it for the wave equation. We're doing it for Laplace and diffusion equations. We see it for advection diffusion problems. Anyway, it's kind of extraordinary. Now, when we started finding this, I asked the question, where might we, how could we construct composite materials where this kind of beautiful behavior could be exploited and get and design composite materials with extraordinary and exotic properties. And I thought back to my postdoc days with Joel Leibowitz at Rutgers in the mathematical physics group, and we were working right when Shechtman was developing quasicrystals. Their Fizerev letter that he got the Nobel Prize for the discovery of quasicrystals. We were the first to look at the questions of classical transport in quasi-periodic geometries. So here's a quasi-periodic checkerboard. This is the arrangement of atoms. This is like a potential energy map for atoms in a quasicrystal. And then here's also a Penrose tiling. And what we did, though, we found some really interesting stuff. I think that looked, deceptively simple. We looked in one dimension, a local conductivity of 3 plus cosine x plus cosine kx, and then the homogenized conductivity has a very strange behavior. If k is rational, then this is a periodic function, and it depends on k. But if k is irrational, then the effective conductivity is independent of k. So this is a very interesting function that I teach in calculus. It's actually continuous at the irrationals and discontinuous at the rationals. And then as I went further with Joel and Shelley Goldstein, we developed what I guess is called a cut and project, now called cut and project, where we constructed a 1D quasi-periodic system by taking a 2D checkerboard and passing lines through it. But you can then take a 3D checkerboard and pass a plane through it. And then it turns out for the 1D case, we can calculate it exactly. And then the graph of the homogenized parameter as a function of k has all this fascinating structure that, to be honest, we have yet to really delve into. And it's a great, I think will be a great undergraduate project, actually. So, okay, so then I had a PhD student, David Morrison, who was in physics. And actually, I went to Antarctica with his dad back about 35 years ago. That's how I knew him. And anyway, so he was just brilliant. And he came up with this. I wanted to pursue these cut and project methods to see, what kind of behavior we would see with this random matrix theory in the context of these quasi-periodic media. But then David had a much better idea where he looked at moire patterns. In other words, take a mathematical lattice and twist them relative to each other, twist and expand. So you have a parameter space of R, and the expansion parameter and the twist angle. And then that provides a template to lay down two different materials. And then this is very similar to like these driftwood fences. You see these moire patterns. But then this gets into quantum dots, artificial atoms, all this really fascinating stuff that's been going on in condensed matter physics in the last 10, 15 years, in particular twistronics. Namely, there's graphene, and then you can take two layers of graphene and twist them relative to each other, get superconducting states, all kinds of fascinating behavior. And we didn't realize it at the time. It only came out in the review process that what we developed, these moire, what I guess I call moire metamaterials, are extremely similar to these twisted bilayer graphene and stuff. And so I then termed what we discovered, the materials, I called them twisted bilayer composites, because it's not at the atomic scale, it's at any scale, and also it's any classical transport coefficient, not just conductivity. So we published this paper, Order to Disorder in Quasi-Periodic Composites. We should have called it a new class of materials, twisted bilayer composites. But anyway, we didn't see that at the time. And again, it's inspired from our CI studies. I guess they're tunable moire composites with exotic properties. This is just a very small, there's an entire zoo of materials that you can generate depending on the twist angle. And so here, note twist angle 0, and this is just a 2-degree change in the twist angle. And we go from bands and gaps in the spectral measure to what looks like purely random behavior, where the spectral measure for this quasi-periodic deterministic medium looks almost identical to the spectral measure at percolation for the random resistor network. Anyway, there's a lot to discover here still. In other words, I think we opened this door and we kind of look, you can see all this amazing stuff, but we have yet to really thoroughly investigate this whole class of, I guess, moire metamaterials that we've opened up. Okay, so at the mesoscale then, also advection diffusion problems are very important in the sea ice business. So here we have the advection diffusion problem, homogenize this, and Andy Maida and Marco Vellaneta were the first to take the functional analytic framework that George Papanikolaou and I developed and apply it to develop Stieltjes integral representations for the advection enhanced diffusivity. Here's showing some of these tracers moving around in the ice. These are some experiments that I did a long time ago. This is kind of what the Stieltjes integrals takes a slightly different form, where now instead of the geometry of the composite, it's the geometry of the velocity field gets embedded into the spectral measure, and the Stieltjes integral representation takes on a slightly different form, but it has all the same basic mathematical hallmarks. And actually here, we were the first to develop a rigorous mathematical theory of the thermal conductivity of sea ice, but where fluid is moving around. There had been theories of pure diffusion before, but nobody had ever rigorously incorporated the convective effects. And so we published that a couple of years ago, and this is the cover of the Proceedings of the Royal Society, showing my some of my dye experiments where they show off the convective structures that you see in sea ice. And these are some of the rigorous bounds. Getting the data is very hard. This was done by Trodal and all a long time ago. And these are our rigorous bounds. And so these are some numerical simulations. And we were assuming this cat's eye flow to model the brine convection, basically. Another very large research program that we have going on is wave propagation through this. And another PhD student, Christian Sampson, was able to push this Stieltjes framework through to get Stieltjes integrals for the effective complex viscoelasticity of the upper layer of the ocean as a two-phase composite of ice and ocean. And the interaction of waves with sea ice is a very important process in the polar regions. It helps determine the growth and the melting of the ice. And actually, my mathematical grandfather, Joe Keller, was the first back at probably, I think, the 1950s, actually, to write a mathematical paper on the interaction of ocean waves with ice flows. And this complex permittivity, up until our work, people had only fit it to data. We were the first mathematical theory of this. And then Daniel Hallman, who just finished last year, he sort of, again, pushed this a lot further, but then developed what I guess we call phononic metamaterials, and investigating all this beautiful random matrix theory and Anderson localization in this context. And so here's some of our localization studies showing mobility edges as a function of the different kinds of eigenvalues you have. And in particular, this is what's particularly interesting, though. This is all the same material, but looking at the difference in scale. And we have yet another mechanism for transitioning in the eigenvalue spacing distribution from Poisson to Wigner-Dyson. And again, this is, we just have a preprint that's just been posted. And anyway, so we hope to investigate this further. Whoops. And of course, the ice pack itself is a fractal. So this really involved, the fundamental problem here is wave propagation through a fractal microstructure. And here's like a photo of the ice pack, and then take that little photo and blow that up, and you see pretty much the same picture. Now, another aspect of all this um, again is the at this mesoscale is the presence of bacteria of algae, and we're interested in trying to improve the models that describe the evolution of these algal communities. And I should mention that 80% of a polar bear's diet can actually be traced back to the algae, not algae living in the ocean, but algae that specifically lives inside the sea ice. And so here's just a very simple model, a dynamical systems model, because I know that's one of the main topics of interest to this group. So I included this. Um, an NP model of nutrients and phytoplankton. However, again, just like Clara was doing with uncertainty quantification in composites, here we're assuming now that the growth rate is a random variable. However, that turns for full-blown biogeochemical models, the Monte Carlo simulations become unwieldy. And so Jody Reimer, who was a postdoc of mine, and now she's an assistant professor at Utah in both math and biology, she led a beautiful study of introducing polynomial chaos methods to this ecological model here with random coefficients to basically to try to understand what's really going, what happens to the algae bloom if you do it the right way. Because what goes on in the literature is people plug in the mean values. And we found that can really give the wrong answers. Namely, here the green is if you just stick in, that's the algae bloom. If you just simply stick in the mean value, but then what is actually going on in the honest to goodness system is the bloom height is about half the height, and it lasts a lot longer. So anyway, this uncertainty, these polynomial chaos methods were very useful in trying to discern what's really going on in these dynamical systems models with random coefficients. Another interesting project that again was started as a simple undergraduate question, namely as the polar bears spend five times the amount of energy by swimming versus walking on the water. So, but we're losing the ice. So, how do polar bears optimize their movement to save energy and survive? And of course, they're wandering around in a fractal environment. Of course, let's keep that in mind as well. And anyway, so this is the cost function, how much it costs as a function. So basically, instead of keeping the 5-to-1 ratio, we went to a infinite ratio to maximize and really study the effect of the connectivity of the ice flows. And we discussed, so basically then the cost to the polar bear, it's expensive. If it's all water, it's very expensive. Then the more ice you get, the less expensive it gets. And then finally, at 0.59, that's the percolation threshold for, the site percolation threshold for the checkerboard. That's where it goes to zero. Almost, you can see it exactly here. This is a larger sample than that. And anyway, however, so it's just like percolation theory. So basically, then I looked at this and said, oh, I bet there's a critical exponent. So we measured the critical exponent, and the critical exponent that describes the vanishing of the energy cost to a polar bear matches almost exactly to the 2D conductivity universal lattice percolation conductivity exponent. So anyway, that again opens up a whole new set of investigations. Is it a new universality class? What's really going on? Anyway, this is a fascinating study, and this is some of the optimal pathways using our algorithms not in the checkerboard, but in actual ice environments. Okay, so another area that we've studied a lot is melt ponds, as I've mentioned before. And I looked at these and say, hey, they look like fractals. And so that's what first got us into fractals, actually. And we discovered that melt ponds exhibit a transition in the fractal dimension, or a transition around 100 square meters from 1 up to 2, where this is like the boundaries behaving like a space-filling curve. And again, one of the simplest initial models that really does a good job is here's the surface topography of the ice, and then we look at the level sets, intersecting the surface of the ice with a horizontal plane and then moving that plane up and down. As the plane moves up, the ponds grow and become more complex. And indeed, we get a nice match for the fractal dimension transition from this model. And another interesting set of questions that this opened up was topological data analysis. In other words, as we move that plane up, then we start with basically we just hit the minima. Then we start hitting minima and saddles of the topography, and then we finally hit maxima. And from that, we can measure the Euler characteristic curve as a function of the height of the plane, basically. And we find an amazing result that the Euler characteristic curve, as we average over 500 different realizations, that the zero of the Euler characteristic curve matches exactly the height of percolation threshold. And this has been found in some other fields, actually, or at least it's been alluded to, I should say. So anyway, this relates two different fields of mathematics, namely percolation theory and sort of aspects of algebraic topology. And anyway, again, another very interesting set of ideas to investigate. One of my favorite models that we developed for studying melt ponds was the Ising model, again, connected to quantum mechanics. Spin up or spin down, or ice versus water. Here's magnetic domains in cobalt, Arctic melt ponds. Magnetic domains in cobalt, iron boron, melt ponds. And the idea is that in magnets, the spins want to align to minimize the overall energy, and so you get these regions of like spins, and that look just like the melt ponds. And so we've developed this Ising model. Instead of spin up and spin down, we have water and ice, and then we start with random initial configurations. And then as the Hamiltonian energy is minimized by Glauber spin flip dynamics, the system flows towards these metastable equilibria. There's the Ising model. Here's our real melt ponds, and we can do an excellent job of predicting the fractal transition. Okay, finally, the last thing I'll talk about is just what's going on sort of on the very big scale. One of the really interesting phenomena that I came across was looking at GPS data of ice flows, and they undergo like Brownian motion. However, it's not just Brownian motion. They exhibit anomalous diffusion with a Hurst exponent bigger than 1 for super diffusion, less than 1 for subdiffusion, and alpha equal 1 for pure diffusion. And we've developed a flow scale model for this, where we can start to mimic this type of behavior. And how does the advective contributions, the currents and the winds affect this? And also there's a jamming transition, which we see. So here's the Hurst exponent. And then also this is, I guess, a jamming transition. When it gets above about 70%, things just kind of jam up and the Hurst exponent goes to 0. And part of what my idea was to treat an ice flow like Einstein's pollen grain and do that calculation, basically. And that's kind of that's been guiding us, basically. This is showing some of the advection. We can actually then use our Stieltjes representations to calculate the effective diffusion coefficient, and we get beautiful correspondence of those rigorous bounds, of these Stieltjes bounds, with our calculations of the large-scale advection enhanced diffusion coefficient, I should say. And then finally, there on the grandest scale, there's the marginal ice zone, which is the transitional region between dense pack ice, bigger than 80% concentration, and open ocean. And this is a very important. It's biologically active, and it's mostly where waves interact with the ice pack. And there's been a lot of questions about. There's been a lot of interest in this because it undergoes a dramatic annual cycle where the MIS moves to the north in the Arctic by 1,600 kilometers in the summer, and it widens by a factor of 4. And we wanted to develop a model to predict all this, to understand all this. And so my colleague Court Strong in atmospheric physics. He thinks like a mathematician. Anyway, he came up with the idea of treating this transitional region as a mushy layer. Mushy layers come up in geophysics and material science. It's a region of coexistence of solid and liquid, like illustrated here. And actually the boundary of sea ice on the centimeter scale, that's a mushy layer, where you have the brine inclusions in the ice. And so we came up with we adapted the physics, the equations of mushy layer physics, and adapted it to on the scale of the Arctic Ocean. And lo and behold, our model then captures this dramatic annual cycle and is able to, and actually we're taking this further now and trying to look at the long-term behavior of the MIS. This is kind of, and then also for you fractal aficionados out there, here's the winter MIS, but here's the summer MIS. And I noticed that, oh, in the summer the boundary looks a lot more high perimeter or fractally. And so I contracted another undergrad to start looking at this and developed into a beautiful project that we published last year in Environmental Research Letters, where we found an almost identical pattern every year that the fractal dimension of the boundary of the MIS obeys. And what's so important about that is that the way waves and heat interact with fractal boundaries is quite different than interacting with smooth boundaries. So this has implications for wave ice interactions and thermal fluxes and so on. And actually, and again, at this oceanic scale, another thing is that's called the polar data gap, where the way satellites work, you can't fill in right over the North Pole. And prior to the recent period, everybody just assumed that there was 100% ice there. But of course, we found that it's not. We're losing a lot of ice even at the North Pole. And so we developed an inverse method by assuming, similar to what we do here in this mushy layer model, but that the sea ice concentration field is a harmonic function. It satisfies Laplace's equation plus some uncertainty. We add some stochastic terms, and then that we learn what those stochastic terms are by looking at the variability in other regions to learn. And anyway, we get a beautiful reconstructions of the completing the data record, and then now the Norwegian Meteorological Institute is using our methods to complete the record of sea ice concentration over the satellite era. So in conclusion, our research is helping to improve projections of the fate of Earth's sea ice packs and the ecosystems they support. And hopefully you've seen that we wind up coming into a lot of areas of mathematics that we didn't necessarily expect, but by studying sea ice, we're advancing the theory of composites, inverse problems, and metamaterials, and so on, and that we wound up in some kind of unexpected areas of math and physics. This is a review paper in the notices of the AMS, goes back to 2020. And then I guess in 2024, I brought a lot of students to the polar regions, to both the Arctic and the Antarctic. We had our first Arctic Mathpedition in 2024, where we brought 7 students from high school to PhD up to the Arctic. This was on our way to the grocery store. Fortunately, we were not on the polar bear shopping list, so none of the students got eaten, and everybody was okay. This is out on the ice, setting up our experiments. This is coring the ice and pouring dyes and stuff there. This is in our abode, cooking and working in the lab. And this is some of the critters that we were able to extract from the sea ice. And finally, thank you to ONR and to NSF for funding our research. So thanks very much for listening, and I appreciate it very much. Thanks again.
Thank you very much, Professor Golden, for this wonderful and inspiring lecture. Are there any questions for the speaker?
A question. Very inspiring talk, Ken. That was great. And on the topological data analysis, you're looking at the Euler characteristic. If you were to look at just the max or the mins or something more like the H0 or H1, is there information in that, or is it the Euler characteristic that is?
That's a good question. I mean, to be honest, we're sort of in exploration mode, in terms of, I mean, ultimately what we'd like to do is to compute the fluid permeability, the physical characteristics, the physical properties, and approach this from the computational topology point of view. That's one of the goals here, especially with Lou Kondich and at NJIT. I guess what happened was there's a whole nother sort of part of this investigation where we first got pulled into Morse theory, where we found that there's these theorems about that the topology can only change at a saddle, and so we really started studying saddle points, and then from the saddles, I guess the PhD student who was working on this, she just got involved, started thinking about Euler characteristics because of this. The sheer importance, because it was the saddles that were driving the transition in the fractal dimension. That was what we were looking at. Actually, there's some slides I'm not showing you. Was we studied the isoperimetric ratio, like the perimeter to the area, and we could measure that as in this model. And then the very moment the water would reach the saddle point, that's when the isoperimetric ratio would jump up, and it just kept jumping. And that's what was driving the fractal transition. And so again, it was all about saddle points. And so our focus on saddle points naturally led us into the Euler characteristic curve. So that's kind of how that evolved.
Nice.
Any more questions?
Yes. Can I? Okay. Thanks. I'm Carlo Cattani from Rome, Italy. Let me first thank you for this excellent lecture, and I'm very glad to be here and lucky to listen to you. You explain so many things about ice dynamics. So I have several questions, but only two in particular. So do you see connections between percolation transition in sea ice and other random media problems, such as transporting porous materials or these other quantum systems?
Yes, absolutely. In fact, certainly the connection with porous media is very close. In fact, this original curve, Katz and Thompson, for the fractal behavior, that was discovered in the context of sandstones, and in particular also this studying the fractal properties and this model here. In fact, I learned about this model, the surface topography and looking at the level sets and so on. I learned about that from the diffusion in turbulent plasmas from Isachenko, Reviews of Modern Physics. It's an amazing paper, about 100 paper, a beautiful review paper of lattice and continuum percolation theory. But in particular, the model that's closely, in fact, some of the results that we got, we're able to apply to electronic transport in disordered media. So you have like a 2D potential function, and then the electrons, they have to have their energy has to exceed a certain threshold in order to be able to propagate through, so they don't get stuck in local minima. And so what we're doing here, this particular model, the level sets of random surfaces, it's basically the same problem as a 2D potential and looking at electronic transport. Schlofsky, there's all these names. In fact, even at Utah, I forgot the names of all my, because they've all retired now, but some of this work was actually going on. Oh, Alexei Efros. There's a whole series of Russian solid state physicists that were involved in these kinds of models. And anyway, and that's probably one of the reasons I was so familiar with these models, was because of my colleagues in physics here at Utah.
Yes, I have a second question, more general. What mathematical problem in sea ice physics remain still unsolved, fundamentally unsolved
That's
so far?
I would say the hardest one is
Wow.
what is the macroscopic constitutive law? In other words, you can take a meter cube of ice of sea ice and put and put it into some sort of engineering civil engineering type of instruments or something and measure the elasticity, its bulk modulus, its shear modulus, all those kinds of mechanical properties. But now when you consider the ice pack on the scale of the Arctic Ocean or on the scale of 50 kilometers, and you have forcings from wind and other ice that's pushing on it or currents, what is the constitutive law? What is the effective mechanical property, the shear the shear modulus, the bulk, these kinds of macroscopic mechanical homogenized properties. This is definitely one of the biggest unsolved problems that a lot of people are really interested in.
Thanks a lot. Thanks again.
You're very welcome. Any other questions? Renal, I'm gonna stop sharing. Okay.